All right, so for our first example here, and this is now at a point where we're going to try some stuff. We want to find the surface area generated by revolving this particular function here on this interval of y values. So note that already this is a function of y and not of x. So that means that the formula that we're going to use for the surface area is going to be the integral from c to d of 2 pi x and then square root of 1 plus, and this will be dx over dy. And all that'll be squared there. And then we'll put dy on the end there. So to use this formula, the first thing that we need to figure out is, first of all, we know what x is. It's just going to be 4 times square root of 1 minus y. So that's what this would be. But we need to figure out what is the derivative of this function, x, and what its square is. So we're going to go ahead and figure that out now. Okay. So we know that the derivative of this function with respect to y is just going to be, and I'm going to write this in prime notation here. So we can look at it like this, and we need to use the chain rule. So this will be 4 times 1/2 of 1 minus y raised to the minus 1/2. And then we'll multiply that times the derivative of the inside function here, which would just be negative 1. And so if we clean all that up, this would end up being a 2, because 4 times 1/2 is 2, times a negative 1, so that would be a minus 2. And we'll divide that by square root of 1 minus y. Okay. Now, because of that, if we square this, then we'll just end up getting 4 divided by 1 minus y. All right, so I'm going to pause this video because I'm getting some feedback from my computer here. I'm going to fix this and then I'll start this again. All right, so now that we have found what the derivative of x is squared, we need to go ahead and figure out, we'll go ahead and plug everything into our formula for the surface area. So let's go ahead and take care of that now. So this would mean here that surface area is now going to be the integral from 0 to 3/4, because that's what we see here for the low and high y value. Have here 2 pi, and then x is just times 4 times square root of 1 minus y. And then this will also be multiplied by square root of 1 plus, and then we'll write in 4 divided by 1 minus y. And then all that times dy. So now what we will do is work on simplifying this integrand as much as we can, and then integrate. So from here we'll do surface area 0 to 3/4 again, and we know that it's 2 pi and 4, that will just end up being 8 pi. We also know we're going to keep this as 1 over y here, but this second square root here, notice that I can rewrite this as 1 plus, sorry, not 1 plus. This 1 here we could rewrite as 1 minus y over 1 minus y. So that is what I'm trying to get at here. And this will be plus 4 divided by 1 minus y. And so in looking at this, we know that we can add these because now these are like fractions. Well, these are fractions that have like denominators. So our numerator here would just end up being, what is this, 1 plus 4. So that would be 5 minus y all over 1 minus y, and then square root of all of that. So I'm going to erase this and then simplify it just to save some space here. All right, so we're going to rewrite this as just 5 minus y all over 1 minus y. So this will be 3 minus y over 1 minus y. And again, here we know that if we have square root of 3 minus y over 1 minus y, we can rewrite that as square root of 3 minus y over square root of 1 minus y. So I'm going to get rid of the square root sign here. Matter of fact, I'll just get rid of all of that. And we will rewrite this as square root of 3 minus y all over square root of 1 minus y. And I keep on putting 3, but it's supposed to be 5. So, all right. So now that we have that, multiply this times dy. And so now we see that the square root of 1 minus y, that will reduce to 1, and we will just keep what we have left. Okay. So here, this would mean that we have 8 pi on the outside of the integral sign from 0 to 3/4. And we would just have square root of 5 minus y here on the inside, dy. And so now we just simply need to integrate that. Now, we do know that square root of 5 minus y is pretty much the same thing as 5 minus y raised to the 1/2. So I'm going to go ahead and rewrite it like that. So we'll say here, and this is 5 minus y, all that raised to the 1/2. Okay, and then from there, this looks like a simple substitution rule type of problem. So from here, we'll go ahead and say let, and I'll use u. Let u equal 5 minus y. And so if we do that, then of course if I take the derivative of u with respect to y, then I'm going to have du over dy is equal to derivative of any constant is 0, and the derivative of minus 1y is just minus 1. So this means here that du is going to be equal to minus dy, which essentially just means here that since we're trying to replace dy, that minus du would be the same as a positive dy. So we have that in place. Also, since we already know what u is, we could go ahead and figure out what u of 0 and u of 3/4 would be. And so u of 0 would just be 5 minus 0, which is 5. And we'll say that u of 3/4, this will just be 5 minus 3/4. And when we do this, this will be 20 minus 3, which is 17 over 4. So now we can replace 0 with 5. We can replace 3/4 with 17 over 4. And we can replace 5 minus y with u and dy with minus du. Okay. So therefore now, surface area is just going to be equal to integral of limits of integration from 5 to 17 over 4. Of course, we still have the 8 pi there. I'll put that back on the inside here for just a second. And this will be multiplied times u raised to the 1/2. And then, of course, we have a minus du in place of dy. So we'll just say this is dy like that and put the minus here. Okay. Now, if we think about our limits of integration here, notice that 17 over 4, which is 5 minus 3 over 4, is smaller than 5. So this negative is popping up here because, of course, our numbers are out of place. So what we can do is rewrite this as 5 for the upper limit and 17 over 4 for the lower limit, and just have this as 8 pi u raised to the 1/2 du. And then, of course, from here, we can just integrate that or take the antiderivative of the integrand that we have directly. Okay. So if we do that, then of course we have the 8 pi, that's a constant. And if we take the antiderivative of u raised to the 1/2, that is just going to be 2/3. And this will be u raised to the 3 over 2. Because again, we're adding 1 to the exponent and then dividing by 1/2 plus 1. And then we evaluate that from 17 over 4 to 5. And so from here, it's just a matter of plugging in everything and getting to the finish line. So this will be 16 pi over 3. And we'll evaluate this at 5 first. And so just to kind of shorten up, we would have square root of u cubed here, which would be the same thing as square root of u squared times square root of u. And this square root of u squared would be absolute value of u. But here, since u will be all positive numbers here, we can just simply rewrite this as u. Okay, so I'm saying all this to say that this is going to end up just being u times square root of u on the inside here. And it's going to be from 17 over 4 to 5. And so now from there, we will go ahead and evaluate. So 16 pi over 3, and then we plug in the 5 first. And then minus, we plug in the 17 over 4. All right, and so from here, we'll just try to simplify as much as we can. The 16 pi over 3, we'll leave this on the outside. It's 5 root 5. And we could rewrite the second term. We just have 17 over 4 times square root of 17 over square root of 4, which is just 2. So this will just end up being 17 times square root of 17 all over 8. And so I'll just go ahead and erase it and rewrite it as that. So this will be 17 times square root of 17 all over 8. Okay. And then from that point, we'll just try to rewrite what we can here. All right, so I'll move this up. At this time, we'll go ahead and multiply through that 16 pi over 3, because that may help us simplify a few things here. So if I multiply the 16 pi over 3 times the 5 square root of 5, 16 times 5 is 80. So I'll have 80 pi square root of 5, all that over 3. And then minus, I know that when I multiply the 16 pi over 3 to the second term, the 16 and the 8 will reduce to just 2. So I'll have a 17 pi here. So I have 17 pi times 2. So I'll just write it because I don't want you all to get confused here. So I'll have 16 pi over 3 times 17 times square root of 17 all over 8. And of course, this is reducing to 2. And then we'll have 2 times pi times 17, which will be a 34 pi times square root of 17 all over 3. Okay, and so I'm going to rewrite all that I have right here as just 34 pi times square root of 17 all over 3. And we'll rewrite this. And there's a pi in there that I'm forgetting. All that over 3. And of course, since both of these have like denominators here, I can just extend this division line and just put that all over 3. I think I'll just redraw it, make it look better here. So this will be all that over 3, and that'll be 80 there. And that will be probably the most simple that we can get this answer to. Of course, if you needed the actual decimal approximation for that, you can just put it in your calculator and figure out what it'll be. The main thing here is that, remember, we are finding an area. So we would have to answer this in units squared. Of course, if we were given the units, then we would be able to tell you exactly what square units that was. All right, so let's move on to the next example. All right, so for this next example, we want to find the surface area of the surface generated by rotating this function x is equal to e raised to the y plus e raised to the minus y divided by 2, which is also known as a cosh function, or a cosine hyperbolic function. And we want to do it from y equals 0 to y equals natural log of 5. So depending upon what you learned in Cal A, if you're, let's say, taking a Cal B course, you may or may not have learned about hyperbolic functions. If you haven't, that's fine. You don't necessarily need to know that for doing this particular problem. But just know that what hyperbolic functions are just functions that we use to do linear combinations of exponentials like e to the y and e to the minus y that show up pretty often. And so engineers use it to kind of condense down calculations. So hence that's why we have it. All right. So anyway, we're going to be dealing with the exponential form of this hyperbolic function. So that's why I say we really don't need to know what it is. But the one thing that we do know that we need to know is what the surface area formula is. And again, since we are doing this in terms of y, we're going to use these limits of integration c and d. And this is going to be integral from c to d of 2 pi x square root of 1 plus dx over dy. And we want that derivative squared. And then all that times dy. So now we need to figure out what the derivative of our function x is going to be. So if we take the derivative of x with respect to y, of course we have 1/2 as a constant that we can just ignore. And of course the derivative of e to the y is just itself. And the derivative of e to the negative y is minus e to the minus y. All right, so if this is the outcome for this, then of course, if we were to take this derivative here and square it, then of course we know that 1/2 squared would be 1/4. And we would also have e to the y minus e to the negative y quantity squared. Okay. And so now we need to figure out what that is actually going to look like here. All right, so the next thing that we'll do, since we have to multiply this out, is we'll go ahead and figure out what this entire radicand is going to be, and then take the square root of it. So we'll say, therefore, we'll have 1 plus the derivative of x with respect to y quantity squared. That will just be 1 plus 1/4. And then we'll go ahead and multiply out this e to the y minus e to the negative y quantity squared. And this will be e to the y squared minus 2 times e to the y times e to the negative y. And then we'll add e to the minus y quantity squared. Okay. And so all I really did here, just in case you don't know what I did, I just looked at the e to the y minus e to the negative y as just a minus b, and I squared that. And of course we know that a minus b quantity squared is just a squared minus 2ab plus b squared. So that's where I got that from, just in case you didn't know. All right, so from here, I'm going to go ahead and continue to work this out. So since I have a 1/4 here, and I know all this stuff is going to be pretty much in the numerator, I'm going to go ahead and make this 1 a 4/4 so that I can have a denominator of all 4. Okay, because basically I'm going to do this, write this as 4/4. And so I'll have a denominator of 4, and then in the numerator I'll have 4 plus, and then I'll just be looking at this 1 times. So I'll just work on everything inside of the parenthesis here. Now, one thing that we do know is that this e raised to the y times e raised to the negative y, if we multiply those together, we get e to the 0, which is just 1. So this middle term here is just a -2. And that's good to know. So we'll just end up having e raised to the 2y minus 2 plus e raised to the minus 2y. Okay. And of course, if we look here, we can combine the like terms of 4 and minus 2. So this will end up being e raised to the 2y plus 2 plus e raised to the minus 2y, all that over 4. Okay. Now, one of the things that I want you to notice here is that, notice that inside this parenthesis here, this e raised to the y squared minus 2 e raised to the y times e raised to the minus y plus e raised to the negative y squared. Remember, all that was just e raised to the y minus e raised to the negative y quantity squared. Okay? And basically what I'm trying to get at is, I'll circle this, all of this is the same thing as all of this. And so now notice that the difference in between e raised to the 2y minus 2 plus e raised to the negative 2y and my numerator here is just the plus sign in the middle term. Okay. So what I'm trying to get at here is that this numerator, all of this could be really rewritten as e raised to the y plus e raised to the minus y, all of that squared. Okay. And so we're going to go ahead and do that in the next step. But the whole entire numerator can be written as e raised to the y plus e raised to the minus y, and those two terms added together, quantity squared. All right, so therefore, we'll now go ahead and say that square root of 1 plus the derivative of x with respect to y, quantity squared here. We'll say that all of that is pretty much equal to square root of e raised to the y plus e raised to the minus y, quantity squared, all that divided by 4. Okay? And of course, we could rewrite this as denominator square root of 4, numerator square root of e raised to the y plus e raised to the minus y, quantity squared. And of course, the square root of anything squared is going to give us the absolute value of the expression under the radicand. And of course, square root of 4 is just 2. And because e raised to the y and e raised to the negative y are both always positive quantities, we can get rid of the absolute value signs here. Okay. All right, so here we'll just say this is e raised to the y plus e raised to the minus y, all that divided by 2. Okay, and that is what that final result will end up being. All right, so now we are ready to go ahead and write everything inside of our surface area formula here. So we'll go ahead and say therefore, and we'll switch colors now, and say that the integral from, of course, our c would be 0, our d would be natural log of 5, and this will be 2 pi times x, and of course x is just e raised to the y plus e raised to the minus y over 2. So e raised to the y plus e raised to the minus y over 2. And then, of course, this square root of 1 plus the derivative of x squared. Let's redo that. Okay. All that is just going to be this e raised to the y plus e raised to the minus y divided by 2. And all that times dy. So from here, we see that this 2 here and this 2 can reduce to 1. And we can also pull out this pi and this, divide by 2, or just pi divided by 2. We can pull that constant out and then just deal with what we have on the inside here that's left. Okay. So if we do that, then of course this would be pi over 2, integral from 0 to natural log of 5. And notice that we have e raised to the y plus e raised to the minus y multiplied times itself. And so that's just going to be e raised to the y plus e raised to the minus y, quantity squared. Okay. Now, the good thing is that we already know what that is. Okay. So remember, up here we said e raised to the y plus e raised to the minus y, quantity squared, was just e raised to the 2y plus 2 plus e raised to the minus 2y. Okay, so we essentially have the same thing here. So we know that this e raised to the 2y plus 2 plus e raised to the minus 2y is what that outcome is going to be. And so we'll write it in that form, and in that form we'll be able to take the antiderivative of what remains here. Relatively simple. All right, so therefore we will say our surface area is going to be pi over 2, integral from 0 to natural log of 5, And here this will be e raised to the 2y plus 2 plus e raised to the minus 2y, all that dy. Okay. And so now from here, it's relatively easy for us to take the antiderivative of all three of these terms here. So we'll just say this is pi over 2. The antiderivative of the first term, and using the chain rule, and this is one that we see often, this will just be e raised to the 2y divided by 2. The antiderivative of 2 with respect to y is just 2y. And the antiderivative of e raised to the minus 2y is going to be plus e raised to the minus 2y divided by negative 2. So we'll make this plus right here a subtraction sign. Okay. And all that will be evaluated from 0 to natural log of 5. And so from here, all we just do is just plug in natural log of 5, see what we get, minus, plug in 0, see what we get, simplify the answer. So we are here on the home stretch now. So this will be pi over 2. And first I'm going to plug in natural log of 5 everywhere. So this will be 1/2 e to the 2 times natural log of 5 plus 2 times natural log of 5 minus 1/2 e raised to the minus 2 times natural log of 5. And all that's taken care of using the top part of net change theorem. And so now we do the same thing, but just plug in 0. So we have 1/2 e raised to the 2 times 0 plus 2 times 0 minus 1/2 e raised to the minus 2 times 0. Okay. So for our first term here, notice that we can use our logarithm properties to rewrite 2 times natural log of 5 as just natural log of 5 raised to the 2. Okay. So I'm just going to go ahead and write these in here. So we could rewrite 2 times natural log of 5 here as just natural log of 5 raised to the 2. And of course, 5 raised to the 2 is just 25. We could rewrite that. Okay. Same deal here for the second term. We could rewrite 2 times natural log of 5 as natural log of 25. And here, since we have a negative on this, this will be natural log of 5 raised to the negative 2, or another way that we could say it is just leave the negative out and just do the 2, and it'll be a negative natural log of 25. And so I'll just keep it that way for now. Okay. Now, of course, in these second 3 terms here, I know that e raised to the 0 is 1. I know 2 times 0 is 0. And I know e raised to the 0 is 1 here. So what I have is 1/2 plus 0 minus 1/2. And so all of that together is going to work out to just be 0 in the long run. Okay. So what we're left with here, let me switch colors again. So what we're left with here is 1/2 e raised to the natural log of 25. And if you remember your logarithm properties, you have one that says a raised to the log base a of x is just x. And of course, if we replace our a's with e's and change log base e to natural log, then we see that e raised to the natural log of 25 is just another way of saying 25. Okay. And so this, of course, will be natural log of 25 here, and this will be 1/2. And so here this would be the same as saying e raised to the natural log of 1/25. So we could erase this negative here. I wanted to wait until this step to do that. So we could look at it like this, and now say that e raised to the natural log of 1/25 is just 1/25. Okay, and of course we have the minus 0 from those other three terms. All right, so from here we just need to take what we have here and simplify it as much as possible. So the first thing I'm going to do is try to combine like terms. And so I see here I have a 25/2, and I have in this third term here 1 divided by 50. So I'm going to make a common denominator here, and just trying to say this is 25/2, but I want this to have a denominator of 50. So I'm going to multiply a numerator and denominator by 25. I'm going to say minus 1/50 here, and then I'm going to do plus natural log of 25 here on the outside. So I just switched the order of the terms there. Of course, 25 times 25 is 625, and so this first term here would just be 625 divided by 50. Okay, so I'm going to erase that and just put that in. So this would be 625 divided by 50. And of course, 625 divided by 50 minus 1 divided by 50 is going to give me 624 divided by 50. And so we'll go ahead and write that in the next step. So this is 624 divided by 50 plus natural log of 25. And we'll go ahead and put the pi over 2 on the outside here. All right, so at this point, what I'll do is, since I know that 624 and 50 are even numbers, I'm going to take the implied 1/2 that's here and multiply it through to both terms. So if I do that, then what I'll have here is 1/2 times 624. Whoa, pen went out of whack there. So 1/2 624 divided by 50. And here I'm going to rewrite, I'm going to put this as 1/2, but I'm going to rewrite natural log of 25 as 2 times natural log of 5 again. And I'm doing that because I know that these two 2's right here will reduce to 1. So now that I have that, of course, I have pi here. And of course, half of 624 would be 312. And that'll be divided by 50 plus these 2's reduced to 1. And then I'll just have natural log of 5 there. And then lastly, if I was to divide, well, we see that 312 and 50 have a common factor of 2. So if I divide 312 by 2, I'm going to get 156. And of course, dividing 50 by 2, I get 25. And my result here ends up just being pi times 156 divided by 25 plus natural log of 5. And so again, since this is an area, I want to answer this as square units. And so this will be my final answer there. All right, so for our next example, we want to take the surface area obtained by taking the function y is equal to the square root of x. from x equals 0 to x equals 2, and we want to rotate it about the x-axis. So if you look at this, this kind of looks like the nose cone of an airplane or a missile or something like that. So this function, square root of x, we may have a missile or an airplane that aerodynamically works out well if we model the nose cone of it by this function. So that's kind of why they're giving it to us here. So since we are rotating about the x-axis, we want to use the surface area formula from a to b, 2 pi y square root of 1 plus dy over dx. And we want to square that derivative dy. So this is the formula that we want to use for that. Just like before, we need to figure out what the derivative of y is and then square it. And then after that, just use that information in our formula here. So I'm going to go ahead and work on that now. So we know that y is equal to x raised to the 1/2 if we look at it in fractional exponent form. So that means that the derivative of y with respect to x is just going to be 1/2 x raised to the negative 1/2. And of course, if we square that, what we will end up getting is 1/2 times 1/2 will be 1/4. And if we take x raised to the negative 1/2 and we square that, we will just get x raised to the negative 1. All right, and so simply speaking, this would just be 1 divided by 4x. Okay. All right, so now that we have that information here, we can go ahead and use that to figure out what 1 plus the derivative of y with respect to x squared is, and then take the square root of that and basically figure out what this integrand is going to be. So we'll go ahead and I'm going to switch colors here. And so we'll say, therefore, now we have 1 plus dy over dx squared. This is 1 plus, and we have our 1 divided by 4x here. And we could look at this as just this 1 here. We could look at this as 4x over 4x if we want. This would be 1 over 4x. So this would be 4x plus 1 all over 4x. And thus, if we needed to take the square root of all of that, then here I'm just going to go ahead and put my square roots over each of these. Make this a little easier. And I know that my numerator and my denominator can be written like this. And of course, this square root of 4 is just 2. And so 1 divided by 2 is just going to be 1/2. And the rest of this, I'm going to go ahead and put back under this square root here. Oh, actually, what I'll do is I'll keep it separate, because it'll actually probably work out better that way if I do it that way. And you'll see what I'm saying here in just a second. So we'll do it like this. Okay. All right, so now that we have that, we already know what this square root of 1 plus the derivative of y with respect to x squared is. We know that y is just square root of x. And of course, when we write all of that, so therefore, surface area is just going to be integral from, and our a to b will be this a and this b here. So it'll be 0 to 2. We'll have 2 pi. Our y is square root of x. And the rest of this is just 1/2 times square root of 4x plus 1. All that over square root of x. And all that times dx. And Don't know why I have dy there, probably because I'm doing the last couple problems with dy. But yeah, I need to switch that and make that a dx right here. All right, so let's go back to this color here. So now we know that this square root of x and that square root of x will reduce to 1. And this 2 here and that 2 there will also reduce to 1. And what we have left is just this pi and this square root of 4x plus 1. So that is what we are going to write here. So we have all of this. We have pi, integral from 0 to 2. And we just have square root of 4x plus 1 dx. And so we just need to take the antiderivative of square root of 4x plus 1. And again, this is another substitution rule type situation. So we can just let u equal 4x plus 1, find a derivative of it, rewrite everything in terms of dx, change our limits of integration to be in terms of x to being in terms of u, and then we can finish out the problem here. So we're pretty much on the final stretch here for this particular problem. So I'm going to switch colors again. So I'm going to say let u equal 4x plus 1. And that's going to imply that du over dx. And let's make that u look a little better. So du over dx is just going to be 4, because derivative of 4x is just 4, and the derivative of a constant is 0. So this means that 1/4 du is just going to equal dx. Okay. Also, since we're changing the variable here, we might as well go ahead and write all these x values in terms of u. So we have u of 0. And remember, u is just 4x plus 1. So we're going to plug in 0 for x there, and that's going to be 1. And we also know that u of 2 is going to be 4 times 2 plus 1. And that will be 9. So now that we have that, we can now say that our surface area is now going to be the integral from, and instead of 0 to 2, now it's going to be from 1 to 9. So 1 to 9. And we have here square root of u. And in place of dx, we have 1/4 du. And of course, if we rewrite all of that, make it look nice and usable, we could rewrite it this way as 1/4 integral from 1 to 9 of u raised to the 1/2 du. And so now all we have to do is take the antiderivative of u raised to the 1/2, which will end up being 2/3 u raised to the 3/2. And we evaluate that from 1 to 9. And so here we know that this 2 here and this 4 will just reduce to 1/2. So we'll have 1/6 here on the outside. This u raised to the 3 over 2, we've seen this before. This is like square root of u cubed, which just ends up being u times square root of u. When we think about that, and again, because our values here for our limits of integration are all non-negative, we can assume that this square root of u squared, which ends up being absolute value of u, will just be u. So saying all that to say, we're here, get this from 1 to 9, and now we can go ahead and plug in 9, and then plug in 1 using the net change theorem from Cal A. So this will be 1/6, 9 square root of 9 minus 1 square root of 1. And of course, square root of 9 is 3. and square root of 1 is 1 times 1 is 1. And of course, 9 times 3 is 27. So this ends up just being 26 over 6. And this ends up having a common factor of 2. And it looks like my pie got lost in the sauce. So let me go and pick that back up. So let me go ahead and here, because I was saying, well, where did my pie go? I was just thinking about that. So I'll just put my pie here, put it there, put it there, put it there, put it there, and then we'll put it there. And so, of course, we take 26 divided by 2 is 13. Take 2 divided by 6, we get 3. And our final answer here ends up being 13 over 3 times pi squared units. All right, so let's move on to our next example. All right, so our next two examples are going to actually involve calculating the surface area for curves defined parametrically, okay? So here we need to define what that is. If you noticed, if you watched the video on arc length, we also did an example to where we had a version of this particular formula for the arc length in a parametric form. And so we have the same thing here. Essentially, if a curve that is rotated about an axis, meaning that the curve sweeps out of the surface, is defined parametrically, meaning that both x and y that we normally use our variables for are defined in terms of another variable, and that inner independent variable is defined on some closed interval such that a, of course, is less than or equal to b. Then we have the surface area that can be computed by this formula. And so again, only thing that we really need to focus on here, because we do know how to find out what the derivative of a function x is with respect to t and the derivative of y is with respect to t if we're given that information. What's different here is that we need to figure out what rho is, or that funny looking p that you see. And so what rho actually is the distance from the axis of rotation that you're taking your function and rotating it around to form the surface area in the first place. It's the distance from there to the element or the arc that we are trying to use to do the rotation. Okay, and so in doing that, it turns out that we have even a more simple, and I hesitate really to say simple, it's a more conceptual formula for the surface area in this case. And it just ends up being, hey, if you can identify what the radius is and you can identify what that bandwidth is, then you could write it that way. Or if you can figure out what rho is going to be, which is the distance from the axis of rotation to the element of the arc, kind of like the radius. And you can find out the differential ds, and I'm going to describe what that actually is. If you can actually figure that out, then we could rewrite this formula this way, okay? And so this picture that I have here sort of explains what's going on here. So, of course, rho is just going to be essentially the radius that you're going to use to take, in this case, the summation of all these little small bands and rotate them about whatever axis that you're talking about. But that ds there, of course, remember from Cal A, that is a differential. And so what you're saying is that is an infinitesimally small change in this s value, okay? And so we define it here as the width of the ith band formed when the element of the arc length is swept out of the surface where it lies, differential for a change in s. And again, that ds just means that it's just the change in s as s approaches 0. Now you're probably wondering, what in the world is s? Okay. Well, if you recall back from trigonometry or pre-calculus trigonometry, remember that S is the letter that they use to define the arc length, okay, which is just a it's just a portion of the distance around a circle. And remember, that was defined as r times theta, where r was the radius of the circle that you were dealing with, and of course theta was the corresponding angle, and that angle would be in radians. So here what we are essentially saying is that ds, in this case, you would be taking the derivative of the arc length with respect to theta, and in this case that would just be r. And so it turns out here that this ds is just going to be whatever your radius is times d theta, okay? Now, of course, depending upon the application, that theta part is going to look a little different, but in all actuality, that's essentially what that ds is, okay? And so we'll see how that looks different here in the next example that we're going to do. So the point I'm trying to make here is that you can use this form of the surface area formula if you just want to identify what is going to be the radius by which you're going to take this function and spin it about the axis that you're going to rotate that function around to create the surface area. If you just know that in your x of t and your y of t functions, you can use this version of this formula that is for parametric type of calculations. Okay. Now, if you conceptually know more of, hey, I have a way to be able to characterize this the bandwidth of this small band here, and I know the radius, but I don't necessarily know per se the actual functions x of t and y of t, then you can use this form of the surface area, okay? So it's two different approaches to accomplish the same goal. So we're going to go ahead and look at this next example here to see how this might work. All right, so for this next example here, I've already worked this one out, but I will talk you through it since it does have some moving parts to it. So this says we want to find the surface area of a sphere. So in other words, we want to basically create a sphere by generated by revolving the circle x squared plus y squared equals a squared about the x-axis. So we're basically generating a sphere by taking a circle that is a two-dimensional figure, and we're imagining that we can take it and rotate that circle about the x-axis, okay? Now, notice that a circle in and of itself is not a function, so what we're going to have to do is really just look at this circle. We're going to have to look at a semicircle, okay? Because semicircle, mainly from this point here, which would be your minus a0, to this point here, which that point would be a0, we would want to either look at the bottom half of this circle or the top half. And just for simplicity's sake, we will look at this top half, okay? Now, realize that this circle here is a circle that is centered at the origin with a radius of a, where a is assumed to be greater than 0 since it represents a distance, okay? Now, if we look at this equation of a circle here, we also know that if we were looking at, let's say, x squared plus y squared equals 1, we know for a circle, the x coordinate for any point on the unit circle would end up being cosine of some angle. So this would be like cosine squared of theta. And of course, the y coordinate for any point on the circle would be sine. So this would be sine squared theta, and that would equal to 1, okay? Now, the point that I'm getting across here is that if my radius is 1, because this is 1 squared here, and I just have cosine squared here and sine squared here, if I have a squared, then that means that my x here is going to be a times cosine theta, and my y is going to be a times sine theta, okay? So looking at that, we know that this equation can be rewritten this way, which means that we can extract out that x is now a function of theta, and that y is actually a function of theta, okay? Now notice that both x and y are defined in terms of another variable, mainly the angle theta, okay? And of course that angle theta would be the angle that's formed from its initial side being the positive x-axis to whatever this terminal side will be, okay? So the circle that we have drawn here is kind of serving its purpose, okay? I'm going to erase some of this, so now that we kind of know what's going on here. Now, if we consider that top half of the circle again, like I said, if we consider this top half here, and this is minus a, and that's a there, then we know that our angle theta will be from, can be anything from 0 to pi, okay? So we know that, okay? Now, if we take the derivative of our function x, which is a cosine of theta, and the derivative of y, sine, y, which is a sine theta, if we take the derivative of those things with respect to theta, then of course, once we do all of that, we'll end up getting a squared sine squared and a squared cosine squared respectively, okay? Now, also note that if I was to sort of rearrange everything here, if I took the derivative of this and then squared it, then, and if I wrote this in differential form, then this would be dx squared, and this would be a squared sine squared d theta, okay? And note here that this would not be a d theta squared, okay? That notation just doesn't flow like that. So this would still just be a d theta here. And of course, the same thing for the derivative of y with respect to theta, and then we square that result, we still just have a d theta here, okay? So now, if we realize that this rho, which we defined as the distance from this circle to the x-axis, that is essentially going to be the y-coordinate for a point on the unit circle. And so I'll go back to the circle that we have here to explain that. So here, remember that this ds is going to be some small piece of the total circle here, just like when we looked earlier here, this ds that was right here was a small piece of the entire function that we had going from x equals a to x equals b, okay? So I'm saying all that to say that since this is, since this is a small piece right here, we've done a change in what my angle started with and what my angle ends with, okay? And here, notice that for any point that's in the middle here from where this angle starts and where it ends to create this ds, any random point in between there is actually going to form this right triangle that you see here with the dotted lines. And so what I've tried to do here is actually zoom in on that some. And so any random point in between the starting and stopping point here, we could take that point and say, hey, at some random angle here, we know that when we stop here, the actual angle difference is just going to be the change in theta, and this ds, which is the change in arc length, is going to go along with this angle right here, which is d theta. Okay. Now, the point that I'm getting at here is that remember that we have these functions that are defined in terms of theta, and so we know that our rho down here is the distance from the circle to the x-axis. So this random point that's right here is a point that's on the circle, and if we go directly down to the x-axis here, then notice that that's one leg of the right triangle that we need. Okay, so that's one leg of that right triangle here. And if we're looking at any random point on this circle, so let's say we kind of got this going on here, we know that the angle from the positive x-axis to the terminal side here, if we form that right triangle, we know that this vertical component here is just going to be whatever this is times sine theta. Okay, so we know that. So we know here that our rho in this particular formula here that we're going to use for surface area is just going to be a times sine theta because of that. Okay. Now, since we know what rho is in terms of theta, we also need to know what ds is in terms of theta. Okay. And so that's why I talked about the arc length earlier. For a circle, we know that the arc length, or the partial distance around the circle, can be characterized by s is equal to r theta, which means that ds is going to be a times d theta if my radius is a. And again, if we go back up here, that's all I was trying to communicate here. Okay, so instead of having an r here, we have an a, which means here, instead of having an r, we have an a. So now what we've done is we've pretty much said, hey, here's a way to describe ds in this formula in terms of theta. And we found a way to express basically the distance in between the thing that we're trying to rotate about the axis of rotation and the axis of rotation. We found a way to be able to express that in terms of theta. So once we've done that, then of course we use the surface area formula. The limits of integration go from 0 to 180 degrees. And here, that's because we are only considering 1/2 of this circle. And we can only consider 1/2 of the circle because just considering either the top half or the bottom half is going to constitute a function. And we need to have a function to be able to integrate. Okay, a function that is smooth and continuous also. Okay, so once we have all that, then of course life is easy. It took us a while to actually get to figuring out what we needed to put into the surface area formula, but once we did that, life's pretty easy. Remember, this is your rho, or the distance from the element that you're trying to rotate and the axis of rotation. And of course, this part is your ds. So now we just take all that information and we just integrate. Of course, our a is a constant, 2 pi is a constant, this a is a constant. So all we have to do is take the antiderivative of sine, which is minus cosine, and we evaluate that from 0 to pi. Of course, plug in pi in for theta, minus plug in 0 in for theta, and we see that we get this outcome here. Of course, cosine of 0 is 1, and cosine of pi is going to be a -1. So that's why we get a negative of -1 here and a 1 there. And all this together works to be 2. And so our answer just ends up being 4 pi a squared square units. Okay. Yeah, again, so I know this problem's a little different than the other type of problems that we've seen, but you see how if conceptually we understand what it is that we have to look for in a problem like this, we could define things parametrically and actually make it relatively easy to figure out what the surface area is going to be, okay? Because the fact that we're dealing with a circle there and we can define things in terms of theta actually made things a little easier than what they would have been if we had been dealing with some other type of function. All right, so let's look at our very last example. All right, so for our last example here, we're also going to consider the line segment that's parametrically defined by a function x of t and a function y of t, where x is just sine squared of t, y is cosine squared of t. And we're going to look at x and y on the interval of t from 0 to pi over 2. And what we're going to do is take that situation there, and we're going to take the result of that and just rotate it about the y-axis, okay? And we want to find the surface area of the shape that would actually do that. Now, the first thing that we need to do is talk about, well, what is x equals to sine squared of t and y is equal to cosine squared t going to look like from t equals 0 to t equals pi over 2. Now you see here I have this line that has a negative slope here, and I'm going to show you how we actually get that. So here, if we just make a column here with t, and then we say x is equal to sine squared of t, and then we do y is cosine squared of t, and we'll say 0 pi over 2. So when t is 0, if we plug in 0 into sine squared, that's going to give us 0. And if we plug in 0 into cosine squared, we know cosine of 0 is 1, so 1 squared is still 1. Okay. So what this means for us is that we have a point 0, 1 on our graph. Okay. Now, we also see here that we have pi over 2. And so sine of pi over 2 is 1. And of course, 1 squared is 1. And cosine of pi over 2 is 0. And of course, 0 squared is 0. So this tells us that we have a point 0, 1 on our graph. Okay. So at this point, we see that if we're looking at our graph, and I'm going to write this two different ways. If we're looking at our graph in terms of x and y, let me do it like that. So we ignore all the t stuff and we just say, hey, x, y. Then of course we have the point 0, 1 and 1, 0. Okay, and that looks linear to us. Okay, now note that if we think about everything in terms of t, then t is an angle. Okay, so I guess another way that I can actually put this to make this make more sense is what we're actually doing here is we're taking, let's say we have this circle that's like this, and we are taking the portion of the circle that is in the first quadrant here, okay, because this is pi over 2 radians, this is 0 radians. So we're taking this and we're trying to rewrite the way that this particular circle is going to act by making it go down a degree, essentially, okay? So my point here, and let me switch back to blue, is that if we think of things in terms of sine and cosine, then we have a circle here, okay? But if we think of things in terms of x and y here, and notice that this is not x is equal to sine theta and y is equal to cosine theta, okay? That's not it, okay? We actually have sine squared and cosine squared, okay? It's just that here when we look at this to begin with, we see that x is defined as sine squared and y is defined as cosine squared, okay? So if we were to kind of put this together here, let's if we look at these 2 points and say, all right, well, these 2 points will be on a line, and I'll tie it together this way. So we know that according to the change, the slope of this line, the change in y values, let's say we go from 1 to 0, the change in the x values will go from 1 to -1, so that'll give you a -1. And of course, since we have this y-intercept here, this tells you that y is going to be -x plus 1, or put another way, x plus y is equal to 1. Okay? Now, if you think about what x is and you think about what y is, remember that x is sine squared and y is cosine squared. Okay? And of course, if we do sine squared plus cosine squared, that also equals 1. And remember that sine squared plus cosine squared equals 1 actually is our way of defining the unit circle parametrically in terms of a variable theta instead of in terms of x. So what we've essentially done is we've taken the unit circle here. So a circle with radius 1. Well, we're looking at this, as cosine of theta and sine of theta. So we're taking this with this angle here, and we've rewritten it in such a way to where now, instead of this being curved, it looks like a line. Okay, so that's what it means whenever we define something parametrically. We put it in terms of another variable to make it look different. Okay. So my point here is that now that we have everything written in terms of x and y, and we know what this is going to look like, we have a general idea of what the shape that's going to come out as a result of having x be sine squared and y being cosine squared for this particular set of angles here. Of course, parametrically, it just looks like this line. And if we take this line and we rotate it about the x-axis, then think about we're taking this shape here and we're rotating it. So what it's going to look like is basically a cone. Okay. And so what we're trying to do is basically find the surface area of a cone. And of course, took a long time to get to that point, but parametrically, that's what we were trying to do, is to rewrite what we understand here in terms of the unit circle, rewrite it in such a way to where we can look at this and say, oh yeah, okay, that's something that's relatively easy to do. We could take that function, y is going to be equal to -x plus 1. We can rewrite it in terms of x being in terms of y. We could rewrite it that way since we're going to rotate about the y-axis. And just simply use the surface area formula for that. Okay, so relatively simple to do here. Now that we kind of know what it is that we're looking at, so I'm going to erase all this preliminary stuff that kind of got you to be able to understand why we even have this graph of this line here with a negative slope going from the point 0, 1 to 1, 0. Hopefully now you understand how we got that. And so when I erase this and continue the video, we're going to go ahead and finish up actually doing the problem. All right, so now that we understand why when we define both x and y parametrically like this using these angles, how the resulting graph will actually look like this line segment here. And if you remember before, we said that this was the line y is equal to -x plus 1 if we're defining this as y in terms of x. If we want to define this as x in terms of y, then of course this would be x is equal to 1 minus y. Okay, and so we'll need to keep that in consideration as well. Now we know parametrically speaking the formula for the surface area, and I actually write it up here, is going to be the integral from a to b, and of course this will be our a and this will be our b in this case. We'll have 2 pi times rho, and remember rho is the distance from the axis of rotation to the element or the thing that we are trying to rotate. Okay, so using that definition here, this is the axis of rotation here, because remember we're rotating about the y-axis. So let's say from here all the way to some point on this line, that is what rho is going to be defined to be. Now, notice that rho goes horizontal, and essentially all it is just a random x value. Okay, so here this is going to end up being our rho that we're going to use. Okay, all right, so we also need to find out, well, what's going to be the derivative of x with respect to t squared, and what is going to be the derivative of y with respect to t squared, and then all that d2. So here, since we already know what rho is going to be, we just need to figure out what the derivative of x is and then square it, the derivative of y is, and then square it. Okay, so let's go ahead and do that now. So we got dx over dt. Of course, that's the same as saying taking the derivative of sine squared, and using the chain rule, that's going to be 2 sine of t times the inside function of sine squared is just sine. Take the derivative of that, cosine t. Okay, which we know this is an identity, and we can rewrite this as just sine of 2t. We take the derivative of y with respect to t, then here this is cosine squared t, and if I take the derivative of that, that's going to be 2 cosine of t times a minus sine t. Okay, and I'm going to clean up that 2 there, and then we'll go ahead and move forward. All right, so from here, notice that this negative 2 cosine t times sine t looks very similar to what we have up here. It's just negative, so we could just rewrite this as a negative sine of 2t if we wish. Okay, so therefore we know that if we take the derivative of x and square it, that's just going to be sine squared of 2t. And if we do the same thing for the derivative of y with respect to t, if we square that, then of course that is just a minus sine 2t, so that's going to end up being the same exact thing. So positive sine squared 2t. Okay, so now what we can do is substitute all this info into our surface area formula. So therefore, surface area formula is integral from a to b. And if we remember up here, our a is 0, our b is pi over 2. So we have 0, pi over 2. And then from here, we have 2 pi. And now notice that rho is our 1 minus y here. Okay, now this is a good thing, but it's also a bad thing. Reason why it's bad is because notice here that we are integrating with respect to t. Okay, since we're integrating with respect to t, we need to have x written in terms of t. Okay, but remember, y is defined as cosine squared of t. So here we know that from this, we can rewrite this as 1 minus cosine squared t, okay? And I'm going to try to make that look a little better. So cosine squared of t here. And of course, we could also rewrite this as sine squared t. And we'll just see which form works better. It may work better to keep it as 1 minus cosine squared. It may work better to do it as sine squared. We'll see. All right, so my point here is that now we know rho is just going to be this x value here. So we're going to go ahead and I'm just going to write it as 1 minus cosine squared t for now. And I'll simplify it to sine squared t if I think that that will actually work out better for us. Okay. So we have that. And so now, of course, now that we know what rho is, we can do the square root of, and then do the derivative of x with respect to t squared, and do plus the derivative of y with respect to t squared. So we'll come and do this now. Derivative of x, when we square this, that'll be sine squared of 2t. And of course, dy over dt is the same thing. So this is just going to be 2 of those on the inside there. All that dt, let's do some separation here. All right, so what we essentially have here is 2 times sine squared of t. So we'll factor out this 2 pi here. Go from 0 to 2 pi there, 0 to pi over 2 there. And we'll keep this as 1 plus cosine squared t for now. And we will look at this as just 2 times sine squared of 2t. Okay. And so if we look at this, I'm just going to kind of go off to the side here and think about what we can write next. We know that since the limits of integration are values of t from 0 to pi over 2, we know that sine is non-negative for those range of angles. So I'm saying that to say that the square root of 2 times sine squared of 2t, we could look at this as just square root of 2 times square root of sine squared of 2t. And since all the values of t that we want to plug into this angle, for these angles here, are going to end up making sine of 2t positive, we know that this would normally end up being absolute value of sine of 2t. But because sine of 2t is always going to be positive for these values, we can drop the absolute value signs, okay? And we can just look at it this way. So essentially, what we have here, all of this will just be square root of 2 times sine of 2t, okay? So now, looking at what we have, notice I could rewrite this 1 minus cosine squared t as sine squared t. So I could go off and do this. Okay. But now notice that what I end up having as a result is sine squared of 2t times sine of 2t. Okay. And to deal with that the way that we need to, if we want to have it in that form, we would have to know something about doing trigonometric integrals. And if you're studying this, you may or may not know that yet. So what I'm going to do is take a simpler approach and just use substitution. Okay. So I'm going to get rid of what we see here, and I'm just going to use substitution because it's a cleaner way to get to the answer that we want. All right, so I've made a little room here after erasing some stuff, and I've also rewritten what we would come out with for this portion here. And we're going to use that to apply the substitution rule here. So let's say let u, we're going to let u equal 1 minus cosine squared of, that should be t there. Let me erase that. Okay, so if that's the case, then we know here that if we take the derivative of 1 minus cosine squared of t, let's get that working, okay, then this will be du over dt. This will be, of course, the derivative of constant is 0. We'll have a minus. Derivative of cosine squared would just be 2 cosine of t times the derivative of the inside function cosine would be minus sine t. So that would make that a plus there. And we know that this, in short, would just be written as sine of 2t. Okay. So therefore, we know that du would end up being just sine of 2t dt, okay, which is exactly what we need here, because all of this would just be able to be written as du, and all of this would just be u. And so the only thing we would have to do now is figure out what is 0 in terms of u and what is pi over 2 in terms of u. Okay, so we'll say also u of 0 is going to be 1 minus cosine squared of 0, which would be 1 minus 1, which would be 0. So that remains the same. And we'll see that u of pi over 2 would be 1 minus cosine squared of pi over 2. And of course, cosine of pi over 2 is 0, so 0 squared is 0. So that would just end up being 1. So now that we have all that together, we can go ahead and wrap things up. So that means now our surface area, the integral will now be, instead of from 0 to pi over 2, it'll be u of 0, which we said was 0, to u of pi over 2, which we said was 1. Okay, so we have that. Of course, we have this factor here of 2 times square root of 2 pi. And here we have u du. Okay, and so really I should just do it like that. Well, actually, to be more precise, I should probably do it more so like this. So we say that times u and put all that in parentheses there, right? And then we can just break this out. Write it like that. And then, of course, taking the antiderivative of u is easy. That would just be u squared divided by 2. And we evaluate that from 0 to 1. Of course, here, this 2 and this 2 will reduce to 1. So that makes life a little bit more simple for us. And let me scroll up here, get a little bit more room. And this will just be pi times square root of 2 here. And we'll plug in 1. So that'll just be 1 squared minus 0 squared. And of course, all that inside the brackets there will just end up being 1. So we see here that we have pi times square root of 2, and this would be in square units here. Okay. All right, so this is what our final answer ends up being. And so hopefully these examples that I've done here even though I know it's been a long video, these problems do get like that. But hopefully by me going through the examples and kind of giving you the gory details of it, of each step, hopefully that'll help you navigate doing your own problems. And so hope this video was helpful, and I will see you in the next one. Take care.